Hello everyone, Dr. Data Science here to teach you data science methods and tools today, tomorrow, and beyond. In this video, I will show you how to handle the class imbalance problem when you train a classifier with a disproportionate ratio of observations per class. This is a common problem in many domains, including computer vision and healthcare. I have posted a series of 5 videos on this topic, and I put a link in the description down below. The difference here is that I will show you how to implement these techniques step by step in Python using Google Colab, which means that you don't have to install Python on your own machine. Before we get started, if you are not subscribed, please consider joining the team. Also, please do me a favor and leave me a comment so I can interact with you and better understand what topics to cover in the future. So now let's start with Google Drive, that you can go to drive.google.com. And now we are going to create a Google Colab file. And here we can find it under Google Collaboratory. If you have never used this, you have to go to Connect More Apps and select Google Collaboratory. But here I have it, and I just create this file. The first thing to do is to just give this a name. I call this Dr. Data Science for obvious reasons. And now the next step is to start importing libraries that we need, such as NumPy, which we use for any machine learning and data science project. Also, in this video, we are going to use the Imbalanced Learn library that has a lot of tools to handle the class imbalance problem. Also includes data sets that we can use to understand the class imbalance problem. So here we see that this is the Imbalanced Learn package, and also gives you information on how to install this, because this is not as common as packages such as NumPy or scikit-learn. We have to make sure that we install this correctly, and that's the information that we have here. So we're going to just use this, and remember that when you have Google Colab and you want to run terminal codes, you need to use exclamation mark at the beginning. So that's why I add that, and then I just run this cell. And one thing that I do in these videos is that I'm going to break down the implementation into different cells so we can exactly see what's happening in each one. However, as you become more proficient, you can just have more lines of code in each cell. It's totally up to you. And in order to run each cell, you need to use this play button or follow the instruction on how to use your keyboard. The one thing that we did here was that we installed this Imbalanced Learn, and I recommend you in these cases go to runtime and restart the runtime. So that's what you're going to do. And if you don't want to see all this text here, you can also go to edit, and you can go to clear all outputs. So now we don't have to stare at those sort of like results that we had before. So now let's start by importing NumPy. You can use it as is, or as you can see here, even Google Colab recommends us to import this as NP. So this allows us from now on to call NumPy NP, which will definitely save time and space. The other thing we want to do is that we are going to use the data set from Imbalanced Learn package. So we're going to say from Learn, that's the name of the package, and then data sets, we want to import fetch underscore data set. So the cool thing about Google Colab is that also it gives you these sort of like autocomplete features that really is helpful in terms of like saving your time, and if you're not exactly familiar with these sort of like names. And to just show you here, so this is that Imbalanced Learn package, and in the user guide, you can see that there's a part that describes about the available data sets. And here in this video, we are going to work with the thyroid data set that gives you the number of samples, features, and the ratio between the number of samples per each class. And also we see one example on how to import this data set, and that's what we're exactly trying to do here, that from inland.datasets, we import fetch datasets. Let's go back to our Google Colab. And so now that we imported these libraries, I've not completely imported them because I've not run this cell yet, but I'm going to also add a few more lines of codes to import this data set, find the data metrics and target values, and so on. So here we can give any name that we want, and I use the exact same name. And we use the fetch underscore datasets. I use, again, the autocomplete feature. And here's the part that you have to give one of the names that we had in that user guide. So here I can just copy paste this. I use this thyroid data set. And this will be imported as the name that we decided. And now we are going to have our data metrics, which is a two-dimensional array where each row corresponds to one sample and each column corresponds to one feature or attribute. So now we are going to have the name of the data set. And if you want to have access to the data metrics, you use .data. So this will be our data metrics. And the size of this will be samples by features. And then we need to also find the target values or labels, which here we have 1 and -1. So we are going to, again, use the name of this data set, and then we use target here. So these are the target values or labels. And just to make sure that we know exactly how many samples we have for each class, we can use one of the NumPy built-in functions, which is called np.unique. And this gives us the unique elements and also the number of elements per each group. So we have, so these are the names that we decide to choose, counts, elements. So now we use np.unique. And we pass the target values or labels here. And now we use return counts as true. So when I print these values, you see exactly what these things are. So I'm going to print for the unique elements and also counts. So now we are importing the data. This may take a little bit while depending on your internet connection. So you can see that here we have two labels, -1 and 1. And we have about 3,500 for the class label -1. And then we have only 231 samples from class +1. So this means that this is obviously a class imbalanced data set, meaning that we have just a few samples in the class 1 compared to the other class. So now, in order to understand how this method performs, if you use, for example, like a standard classifier such as logistic regression, we can use the scikit-learn library. So we're going to say from sklearn, so that's the name of the scikit-learn library. And for this one, you don't have to install anything because this is one of the most widely used like libraries, and it's already available here. And so we use model selection, we import train, test, split. And what this does is that it allows us to get this entire data set and divide these into training and test data sets, as the name suggests here. And also because logistic regression classifier is a linear model, so from sklearn.linear model, we import logistic regression. So we have our classifier, we have a method to divide the data into training and test data sets. So in order now to use the first function, we need to give the names of the training and test data sets. So we have the X train and X test. So these are the data matrices. And then we have the labels for training and test data set, which are Y train and Y test. And now we use train test split. And one thing you can do here is that use multiple lines, so you don't have to have everything in one line. So I just press enter. So this gives me a little bit more space here. So we give the entire data set, the data metrics, the labels, and also the size of the test data set. So here we want to choose 30% of the data for testing, and the remainder, which would be 70% for training. And also because this step involves some sort of random number generation to randomly sample 30% for the testing data, you can specify random state. And here I'm just using, for example, 4. So what this allows me to do right now is that if you run this code again on your machine, then you will get exactly the same training and test data set. So this is really useful for reproducibility, which is an important topic in machine learning. So here what we have done, we had the available data set. I can show you here that we had the entire data set here, and then we divided this into train and also testing. And now we want to train a classifier on this portion of data and see how this will perform on the test data set. So that's like our next goal here. So in order to train a classifier, we are using logistic regression. And one thing you need to do here is to choose the name of the classifier, which I here use the name CLF. That's the common name to use. And now we use logistic regression. And then inside parentheses here, you can decide what to choose for the input arguments that this function accepts. So if you go to scikit-learn and then find logistic regression, here you see a list of all the available input parameters. And some of them might not be really useful, but some of them are very important, and we're going to see one of them today. So in the first example, what I want to do is that I want to use all the default values. That's why I just use these parentheses and I don't specify anything else. And after this, we're going to use .fit, and this means that now we want to train this model on the training data set, and we pass X train and Y train. And then after we do this step, we use prediction, and we use .predict. That's the common way of using scikit-learn, that we use .fit for training the model using the training data set. So that's why here we give both X train and Y train, both the data metrics and labels. However, for the prediction step or the testing step, we only give the data metrics and we don't have to pass those labels. And we use those actual labels, which are also known as ground truth labels, for evaluating the performance of the model, as we will see very soon. So we can run this cell, and we get this warning here about the number of iterations that I'm going to talk about it later. But anyway, this will give me some predicted values. And we can, for example, look at the first 10 predicted values here, that you can see that 9 of them are negative ones, and there's only one that is classified as 1. However, just by looking at this array of numbers, it's really hard to see if this is a good model or not, if we have satisfactory performance. So that's now you have to use evaluation metrics. And that's, again, part of scikit-learn, that if you search for metrics and scoring, you see that for different models, classifiers, regression models, there are multiple ways of evaluating performance. And here, for classification, we use something that is called confusion metrics. So in order to use that, we go from a scalearn dot metrics. We import plot confusion metrics. And also there's a package called Seaborn that has a lot of nice tools to visualize statistical models. And we import this package too. And you're going to see like where we're going to use this. So we want to plot our confusion metrics. So now we're going to call this function. And the way that it works, you can give the name of the classifier, which if you remember, we use CLF. You give your test data and also the ground truth labels or actual labels, because we need this for the evaluation part. And then you can also provide a color map. These are more advanced settings that you have if you want to have a really nice sort of like, plots that you can present. And also we set the color bar equal to false. So now we can run this. So this is the confusion matrix that I've talked about that in those 5 videos. Each row of this matrix corresponds to true labels. So we have -1 and 1, or negative and positive. And then the columns are for predicted labels, -1 and 1 again. So then we will have true negatives, true positives, false positive, and false negative. But before even like discussing this more, you can see that it's a little bit hard to visualize this figure. And one thing that you can do is that's exactly why we imported Seaborn, is that we can decide the style of this figure. So in order to make this easier to visualize, we can say that we want to use this as a poster. So now you can see that we have a much nicer figure or confusion matrix that we can easily read all those numbers. And what this means is that, for example, for class 1, we have a total of 35 plus 43, which is 78 samples. And only 43 of them are correctly classified as 1. And then the remainder are incorrectly classified as negative 1. And you can also use the same sort of like reasoning to understand how many of the data points that they were labeled as -1 are correctly classified. And sometimes you want to also find something that's a little bit easier to understand than these confusion metrics. Obviously, this is very useful, but sometimes you're looking for some numerical values. So for that, we can again go to scikit-learn.metrics, and this time we import 2 important quantities that are called precision and recall. And we have used these and defined these in those 5 videos. So we can use, again, scikit-learn.metrics, import recall score. So one is for precision, one is for recall. And one thing that you can do is that you can write this in only like 1 line, just by simply putting comma. And then the other sort of like a score that you want to import from scikit-learn.metrics. This will definitely make your code easier to read. So here we are now going to find precision. And we use precision score. And you have to give the actual labels or ground truth labels and also the predicted labels. So that's why we have Y test and Y predicted. And similarly for recall, we use the same technique. We have Y test and Y correct. This stands for predicted values. And now we can also use the print function to print these values. So one thing that I recommend to use is that to exactly write what these numbers correspond to. So I'm saying that precision and recall scores are. And then, so we have 2 numbers here that we want to print, but right now I don't know what those things are. So what you can do, you can use these curly brackets and say that we want to have two numbers here, and then use dot format. And here is where you can give instruction on what those numbers are. So we say that number one is precision. I just copy paste this. And number two is whatever the recall value is. So in this case, we don't have to exactly specify what these values are, but as we run this cell and we find these values, now we substitute them here. And now if I run this cell, you see that we get that precision and recall scores are these two numbers. One thing that you can also do, if you don't want to see all these sort of like numbers here, you can say that you want to round this only to 2 digits after point. So you can say around 2. And so this is now much easier to use. So this means that precision is 0.78 and recall is 0.55. And here I'll just very briefly again explain what recall is. So recall is always this number, which is the true positive, which is here 43, divided by the sum of these two numbers. So here 35 and 43. So I can just show you this very quickly, that if I divide 43 by 43 plus 35, then I get that 0.55. But the nice thing is that all these things are implemented. So as long as you know what these quantities are, you can just simply use this built-in evaluation scores, and you don't have to be worried about doing these calculations. So this might not be really good accuracy because, as you can see, for the minority class, which is the patients with the thyroid problem, we can see that we only correctly classify half of them. So we need to improve the performance specifically for the minority class. And what we can do here is that we can go back when we train the logistic regression classifier. So we don't need to change the train test split that we use, but we want to see if there's any way we can make this algorithm better, working with this imbalanced data. And when you go to the page that explains all these features that we have, one of them is this class underscore weight. So what this is telling us that when we are working with imbalanced data, we can adjust weights inversely proportional to class frequencies in the optimization problem, so that when we use this technique, we place more weight on the class with the minimum number of samples. And so that's what I'm gonna do here. So if you look at it, there's this option called class underscore weight, and I'm gonna set this equal to balance. So this means that we are working with an imbalanced data, and we want to make sure that the optimization problem or the cost function that we have is balanced. So we come here, we use class underscore weight. You see that's exactly what Google Colab is showing me here. And then I use this option that is called balance. So this is useful when you're working with imbalanced data sets. So now we are going to train this classifier. And what we can do again, we want to look at this confusion matrix. So let's copy this line. And now, because I call this classifier again CLF, so I can see what happens this time with this new logistic regression classifier. And so now you can see the substantial difference between this case and the previous one. So now again, if you remember, we have 78 samples that they have class label 1. And now 69 of them are correctly classified compared to only 9 of them that are misclassified. So this means that we could substantially reduce the number of false negatives, which is really important in these cases. We can even come here and find the precision and recall values and see if we could get higher recall values. And okay, so what's happening here? This y underscore pred is from the previous case. So we need to make sure that we use this new classifier to make predictions. And that's where we found our predictions. But before that, we use the predicted values from the previous classifier. Now we can have that updated, and you can see that we improved the recall value. And something else that is happening here, you can see that opposite side of the recall value, the precision score gets closer now to 0, which is something that is not favorable. And this is usually what's happening in most cases working with imbalanced data sets. That when you are improving recall, then the precision score gets worse, and so on. So it's really important to find the right balance between precision and recall scores. And that really depends on the application. And I will have some videos in the future to talk about how you can find the balance between these two numbers. But the point that is very important here was that if you use logistic regression classifier and you want to train this on an imbalanced data set, you can use this class underscore weight and set this equal to balance. This will automatically change the optimization problem. And that's why this method is called cost-sensitive learning. So obviously now we can do many other things. We can look at the options that are available, like other options. We can, for example, see that you can increase the number of iterations. That's like one warning that we got in the sort of like the Google Colab that says that we reached the maximum number of iterations. So we can, come here, and in addition to setting class weight, you can also say max iterations from 100 to 1000 and see if that helps. And you can see that now we don't get any more warning because of the fact that now we increase the maximum number of iterations, and the solution will converge to the optimal solution. So we have all those options. I hope you found this video useful, and I want to thank you for watching this video.